Hello. In this video, we will discuss um, the transport of momentum, uh, energy, and mass. So starting out here with momentum, the average momentum carried per particle would be m, the mass time of the particle times the velocity as a function of position, say y. Its transport results in a shear stress. So the flux of momentum is equal to the negative of the shear stress, which is going to be minus alpha over 2 m times n times c bar times L times du dy. Mn is density, and alpha over 2 mn, or density times c bar L, we define as the viscosity. And so the viscosity is 1/2 alpha, and we put a subscript on alpha, subscript mu, to remind us that the alphas for the different uh, transport properties may not be the same. Um, mu is 1/2 alpha sub mu uh, times rho times c bar L. One can show from more advanced theory that alpha mu is about of order unity. And if we use the ideal gas law, we can explore the temperature dependency of the viscosity. And from this simple theory, the viscosity should be proportional to T to the 1/2. Um, and it should be inversely proportional to the diameter of the molecule. So, not surprisingly, the bigger the molecule, the less momentum transport. A better approximation for viscosity is a formula given by Sutherland, and it's shown there at the bottom of the slide. S is a fitting constant, and you can find values for the fitting constant. But needless to say, there are many, many, many empirical formulas for the viscosity of various substances. Um, just a little bit about units. The viscosity of mu is mass over length time, which in SI units is kilograms per meter second. A common unit for viscosity is the poise, which is um, the CGS version of the SI version. It's grams per centimeter second. The centipose is 10 to the minus 2 pose, and you will see viscosities expressed in terms of pose or centiposed or millipose, etc. The kinematic viscosity, which is defined as mu over rho, has dimensions of length squared over time. So in the SI system of units, it would be meter squared over seconds. In the CGS system, it would be centimeters squared per second, etc. And this slide shows a table taken from Engineering Toolbox for the viscosity of various gaseous substances and their dependency upon the temperature. And it's an interesting exercise to plot these and see what the how close the temperature dependence is to 1/2, T to the 1/2. So that's momentum. Now energy, what we are transporting is internal energy, and that can be written for a monatomic gas as mc sub v T. So the heat flux becomes um, minus 1/2 alpha nc bar L times m times c sub v dt dy. And if we gather up everything in front of the dt dy, that becomes the thermal conductivity, which here we have called lambda. And lambda is then equal to 1/2 alpha times rho times c bar times L times c sub v. Or it can be written as alpha for thermal conductivity divided by alpha for viscosity times the viscosity times c sub v. So it is interesting that for monatomic gas, the thermal conductivity and the viscosity are so closely related. So recall various numbers, the Prandtl number, C sub p over lambda, and gamma, which is the ratio of specific heat, so that the Prandtl number can be written as alpha mu over alpha lambda times gamma for a monatomic gas. And For a monatomic gas, the ratio of alpha mu over alpha lambda is equal to 5/2. And so if alpha mu is 1, then alpha lambda would be 5/2. There is a correction called the Eucken correction for non-monatomic gases, and basically what one does is write the internal energy as the translational contribution plus the internal contribution, likewise for the specific heat, and then assume that the thermal conductivity can be written as the sum of a translational and internal portion. And then you get an expression at the bottom, which is lambda is equal to mu times 5/2 times the translational contribution to the specific heat plus the internal contribution to the specific heat. There are many, many, many empirical expressions for thermal conductivity, and if you search the literature for some specific substance, you'll undoubtedly find some. But also, again, we'll be looking at more complete theory, at least for gases. So here's a table. This is from my CRC Handbook of Chemistry and Physics, but the table is generated by Marcia Huber and Alan Harvey, who work for NIST. And the table is actually much more extensive than that, but if I put it on a slide, you wouldn't be able to read any of them. But this gives for a number of substances of varying molecular weight, the thermal conductivity at various temperatures. Finally, how about mass? For mass, the flux is a given species, and for multi-component mixture, it turns out that mass transport is quite complicated. But if we don't have at least two species, then mass flux doesn't really mean anything because there's only one species, and there'll be no net flux of that species other than through the motion of the gas. But we'll look at a simple binary mixture where there are two species, species 1 and 2. So the sum of the number densities of the two species has to equal the total number density. Assume that's constant. If that's the case, then the gradient in one has to be the negative of the gradient in the other. And so the flux of one has to be the negative of the flux of the other. So if we take phi as the fraction, the mole fraction of species 1, so that would be at the number density 1 divided by the total number density, and that is transported by NC bar over 4, then we get the first expression, which is, when we group everything, turns out to be minus 1/2 alpha sub n for mass transport, C bar L for species 1, dN1 dy. Now, you'll get an expression, a similar expression for 2 that is also shown. And then the diffusion coefficient is defined by the relation J equals minus D dN dy, and that's just a gathering of 1/2 alpha C bar L. And so, because of the mass balance, where the fluxes have to be equal to each other of 1 and 2, but of opposite sign, then it turns out that the diffusion coefficients of 1 into 2 has to equal 2 into 1. And in fact, that is not the case, because that implies that the square root of m pi d squared is the same for the two gases, which may not be true unless they're nearly identical. Our result, which is called Fick's law of diffusion, is only valid in the limit of n1 much, much less than n2. And in general, the equations of multi-component diffusion must be used. And we obtain them from the Chapman-Enskog solution to Boltzmann's equation, which we'll get to in a couple of videos. So here are just some diffusion coefficient numbers for common gases. And this is an assumption that the gas is in small concentration in air. So it's the diffusion coefficient of these gases in air. And the numbers are given at the table and for a range of temperatures. And these are from engineeringtoolbox.com. Just a reminder that there are some important non-dimensional numbers, which are ratios of transport properties. So the Prandtl number is the ratio of momentum to thermal diffusion. For air, it's about 0.7. The Schmidt number is the ratio of momentum to mass diffusion, and in air the Schmidt number is about 0.55, and the Lewis number is the ratio of mass diffusion to thermal diffusion, and in air it's about 1.3. And alpha in this case is not the alpha that we were discussing earlier, it's the thermal diffusivity, which is defined as the thermal conductivity divided by the mass density times the specific heat, constant pressure, specific heat. So that's it for this video. Thanks for listening. Have a great day.